Hi, this is John Whitaker for the Mathematical Analysis 2, and this is video lecture number 31. And we had just ended with a theorem that had two parts in video lecture 30, and we had done part A, but not part B. So let's remind ourselves what that theorem was for part B, and then let's prove part B. So the theorem was, it says if K is compact, if C of K, I'm sorry, if F of N, let's write it down, is known of C of K. Remember, those were complex valued functions defined on K that were continuous and bounded. And that's true for n from 1, 2, 3, whatever. And if f sub n is pointwise bounded, and equicontinuous, on K, then part B was, and this is what we're interested in proving, that. Well, let me write down A. It says that Fn as a sequence is uniformly bounded on K. And part P, which is what we want to do, is that Fn contains a uniformly convergent subsequence. It is part B we want to prove, as we proved in part A before, and we're going to use a fact that really we haven't proven. I'm just going to state that it's fact. It's going to help us with this, but before I get to that, for the proof, part B, we're going to suppose K is compact, F sub n are element of C of K. Of course, that F sub n's are pointwise bounded. And equicontinuous. Okay. Now, as a fact, I'll just say that since K is compact, then K has a countably dense subset. Let's call it E. This is the fact I was referring to. We haven't proven that fact, but it is something that's true. We're just going to take it as a fact. Since Fn's are pointwise bounded, on K, then they're pointwise bounded on E. Okay. Then F sub n has a subsequence say, f sub n sub I, such that f sub n sub I of x is a numerical sequence that I run from 1 to infinity, converges for each x in E. To simplify notation, we'll let f sub n sub I be represented by g sub I. Now, we'll let epsilon be greater than 0 be given. Since the f sub n's are fy continuous, on are fy continuous, then the g sub i's are fy continuous. So, by definition, there exists a delta bigger than 0 such that for all x and y in E, or in K, with the distance between x and y being less than delta, then g sub I of x minus g sub I of y will be less than, well, anything that I'd like, so I don't think epsilon over 3. And that's true for all I. As we had before, if we look at the collection of neighborhoods about x for each x in K, this is an open cover for K. Okay. Well, we know K is compact. And since E is dense in K, and what I mean by that is that every neighborhood of any x in K contains a point from E. And K is compact. Then there exists a finite number of points from E say, x sub 1, x sub 2, all the way up to x sub m, such that K is a subset of n sub delta of x sub 1 union n sub delta of x sub 2 union all the way up to union of the neighborhood of radius delta about x sub m. Since the gi sub x's converges for each x, any, okay, then there exists an integer n sub x sub q, we'll say, such that for all I and j bigger than or equal to n sub x sub q, then g sub I of x sub q minus g sub j of x sub q will be less than epsilon over 3. And here's where q runs from 1 to all the way up to m. Okay. What we do is we let n be the maximum of nx sub 1, nx sub 2, all the way up to nx sub q, or nx sub m, I should say. Then, for all I and j bigger than or equal to big N, we have that g sub I of x sub q minus g sub j of x sub q will be less than epsilon over 3. And that's true for all q, right here, equal to 1, 2, all the way up to m. Okay, so here we let x be an element of K. Then, so this is an element of our space K, which we know is contained in that finite union of neighborhoods. So x has to be an element of n sub delta of x sub q for some q equal to 1, 2, all the way up to n. So that g sub I of x minus g sub I of x sub q, that norm is going to be less than epsilon over 3. And that's true for all I. That last statement is due to the equicontinuity of the g sub i's. Okay, so for all of I and j bigger than or equal to this big N, we have g sub I of x minus g sub j of x. That norm is equal to, well, let me put it right here, is equal to g sub I of x minus g sub I of x sub q plus g sub I of x sub q minus g sub j of x sub q plus g sub j of x sub q minus g sub j of x. And we'll use the triangle inequality here. This is less than the norm of g sub I of x minus g sub I of x sub q plus the norm of g sub I of x sub q minus g sub j of x sub q plus the norm of g sub j of x sub q minus g sub j of x. And so this is going to be less than epsilon over 3 plus epsilon over 3 plus epsilon over 3, which equals to epsilon. And so what we have, by the Cauchy criterion for uniform convergence, that means the g sub i's, what we've shown is the g sub i's converge uniformly on K. And that's what we've set out to prove for Part B. Okay. Next, we have a theorem that we want to prove. And this is called the Weierstrass theorem. Weierstrass, I call it approximation theorem. And here's what it says. It says, if F is continuous, or is a continuous, complex function on the closed interval from A to B, there exists a sequence of polynomials we'll call P sub n, such that the limit as n goes to infinity of P sub n equals to F uniformly on A to B. And if F is real, it's a real value function. Then the P sub n's are real values. This theorem Weierstrass approximation theorem says that any continuous function can be approximated, or is the limit, of a uniformly convergent sequence of polynomials. We want to prove this. The proof is got several parts, and here's what it says. First of all, for case 1, I'm just going to have a couple subcases. We're going to assume the interval a to b is 0 to 1. Subcase 1, under this assumption, is that we're going to suppose f of 0 is equal to f of 1, which equals to 0. We'll have this assumption. And so we're going to start off by letting, in this subcase, f be continuous on 0 to 1, and f sub 0 equals to f sub 1 equals to 0. Okay. Then what we're going to do, we're going to define f of x to be equal to 0 for all x that is not in 0 to 1. Since f is continuous on 0 to 1, and 0 to 1 is compact, then f is uniformly continuous. On 0 to 1, and therefore, or I'll just say this kind of in a little bit of a more systematic way. Since f of 0 equals to f of 1, which equals to 0, and f of x equals to 0 for all x not in 0 to 1, then f of x is uniformly continuous. On R. We're going to define a new function, q sub n of x, and it's going to be equal to c sub n times 1 minus x squared raised to the n for n equals 1, 2, 3, and so forth. And c, or where c sub n's are chosen such that the interval from -1 to 1 of q sub n of x dx equals to 1. And that's true for all n. Now, one thing I just want to point out is that q sub n of x is going to be a real value function. Okay? So that's what we have. And by its definition. And what we're going to have is that, note, q sub n of minus x is equal to c sub n times 1 minus minus x to b squared, all that raised to the nth power, so I'm just using the definition here. But minus x squared is the same thing as x squared then. And so what that shows is that q of x, q sub n of x, is an even function, which means q sub n of x is symmetric about the y-axis. Thus, if we look at the interval from minus 1 to 1 of q sub n of x dx, we know that's equal to 1. That's going to be equal to 2 times, due to the symmetry, the interval from 0 to 1 of q sub n of x dx. And that's going to be bigger than or equal to 2 times the interval from 0 to 1 over the square root of n times 1 minus x squared raised to the n. I've made a mistake. Let me back up. Yeah, it's a small mistake. It's easy to correct. What I said was true here about the Qn of x, but let's just look at the let's just, instead of Qn of x, let's look at 1 minus x squared raised to the n, which is also symmetric. So that's the part I should be looking at, which is 1 minus x squared raised to the n. Okay. Now, that's what I should have been looking at. Dx. Okay, look, what I did between going from, I had previously 2 times the interval from 0 to 1. Well, here, this guy is positive, so this is true since 1 minus x squared to the n is going to be greater than or equal to 0 on 0 to 1. And so I'm not integrating as far, so I'm not getting as much of the positive area under this curve. Well, that's equal to, that's less than or equal to 2 times the interval from 0 to 1 over square root of n of 1 minus n times x squared dx. And here I'm basing that on the fact that 1 minus x squared raised to the n is going to be greater than or equal to 1 minus nx squared, and that's true for all n, which can be proven using induction. The book makes a comment about this statement being true, and it doesn't use induction. So you can look at it, but I can prove it using induction. That's what I'm not going to show that here. Now, look, this is equal to 2. This is a polynomial, and it's easy to integrate it. What you get is you get x minus n over x cubed over 3, evaluate from 0 to 1 over the square root of n. Okay. And then that's equal to 2 times 1 over the square root of n minus n times 1 over the square root of n to be cubed over 3. That's equal to 2. Okay. This is 1 over the square root of n cubed is really 1 over n, and then in the bottom square root of n. So this is 2 times 1 over the square root of n minus 1 over 3 times square root of n. And then that's equal to, you get a common denominator, 3 times square root of n. So that's 2 times 2 over 3 times square root of n, which equals to 4 over 3 times square root of n. And I'll just make one last comment. That's definitely bigger than 1 over the square root of n. Now, since, or I should say for, the interval from minus 1 to 1 of c times n, which is 1 times 1 minus x squared raised to n dx, which is the interval of the q sub n, to be equal to 1, that tells us that the c sub n has to be less than the square root of n. Okay. So, for any delta that I'm saying bigger than 0, I'm going to have less than or equal to 1. Then for all x with delta is less than the absolute value of x is less than or equal to 1, then q sub n of x, which equals to the c sub n times 1 minus x squared to n, by definition, which we know to be less than or equal to, of c sub n times 1 minus delta squared to the n, which we know to be less than or equal to the square root of n times 1 minus delta squared to n. I'm just replacing the c sub n by something bigger, because that's what we have. And let us note something about the limit as n goes to infinity, this guy. Square root of n times 1 minus delta squared raised to n is equal to the limit as n goes to infinity of, let's write this down as n to the 1/2 over 1 minus delta squared to the n. And you can see that that's going to the form of infinity over infinity, which we will use L'Hopital's rule on. Okay, let me just point right here. I'm going to use L'Hopital's rule. I'm going to take the derivative of the top over the derivative of the bottom. This is an exponential function, and its derivative is going to be this exponential function times ln of 1 minus delta squared. Okay, and I made a mistake here. I said to the n, but really it should be to the minus n. To pull it down to the bottom, I've got to change the sign of the power. And so that's what we're going to have. Let me write that down. So it's equal to the limit as n goes to infinity of 1/2 over 1 over the square root of n, all over 1 minus delta squared to the minus n times ln of 1 minus delta squared, and then times minus 1, so the derivative of the n. And that's equal to the limit as n goes to infinity of 1/2 times 1 over the square root of n times 1 minus delta squared to the positive n over this number minus ln of 1 minus delta squared. As n goes to, gets really, really big, this goes to 0 and so does this. And so this ends up being 0. And again, that's true for all delta that is bigger than 0, but less than 1. Okay? That's what we got. So, what we can go from here is that there exists a natural number n such that for all n bigger than or equal to big N, the square root of n times 1 minus delta squared raised to the n is going to be less than or equal to epsilon. And thus, this is really true for all deltas in between 0 and 1, and inclusive 0 and 1, really including the 1. Thus, for all n bigger than or equal to n, q sub n of x minus 0 will be less than epsilon. And that's going to be true for all x such that delta is less than or equal to absolute value of x is less than or equal to 1. Okay. Now we're going to consider p sub n. Let's write it down as an integral from -1 to 1 of alpha x plus t times q sub n of t dt. And that's where we're going to have 0 is less than or equal to x is less than or equal to 1. That's our definition for p sub n of x. Since f of x is 0 outside of 0 to 1, then alpha x plus t is possibly non-zero only when zero, this is the word bend here, is less than or equal to x plus t is less than or equal to 1. So that means that alpha x plus t is possibly non-zero. Only when this would say that minus x is less than or equal to t is less than or equal to 1 minus x. And we're solving for t here. So, what that says is Pn sub x was really equal to the integral from minus x to 1 minus x of alpha of x plus t times qn sub t dt. Okay, using the change of variable and here we're going to let u equal to x plus t. We have, okay, so I'm looking, I'm looking at this integral here, and I'm going to let u be equal to x plus t. we have p sub n of x is equal to the integral from 0 to 1. So u was x plus t, and t went from minus x, so that's the lowest it was in the previous interval. So t is minus x plus x, that's 0. Top is going to be 1 minus x plus x, so that's to 1. That's how we got these two. That's what u runs from for the limits of integration. This would be f of u, q sub n of u minus x, and then it would be du. So here's what we have. We have p n sub x is equal to the integral from 0 to 1 f of u c sub n times 1 minus u minus x to b squared all raised to the nth power du. We can see right here, we're integrating with respect to u, so x is going to be there as a constant. It's got powers, and the rest of it's going to be numbers. So here, this is going to be polynomial in terms of x. Okay. Thus, the p sub n's is the sequence p sub n's is a sequence of polynomials, and if f is real, then p sub n is real for all n. Excellent. Now, we want to let epsilon be greater than 0, since f is uniformly continuous. We can choose delta greater than 0, such that for all x and y with x minus y inside norm is less than delta, then the norm of f of x minus f of y, here I've written it down f of y minus f of x, and I notice this probably here, is going to be less than epsilon over 2. So here we let m equal to the suit of the f of x. And here this is over x's element of 0 to 1, which we know exists. Because f is continuous on a compact set 0 to 1. Now, for every 0 being less than or equal to x less than or equal to 1. We have piece of n of x minus f of x in 1 is going to be equal to the interval from minus 1 to 1 of f of x plus t minus, times q sub n of t dt. So that's what p sub n of x was originally defined to be. Minus, now, f of x is f of x. I'll write it down. But I'm going to multiply by a funny looking 1. That's from minus 1 to 1 of q sub n of t dt. Remember, the integral of q sub n of t was equal to 1 for each n because of the choices of the c sub n's. Okay. Now this is equal to the integral from minus 1 to 1 of f of x plus t minus f of x times q sub n of t dt. So we combine it into one integral. And then bringing the absolute values inside, we have the integral, bring them inside. Integral from minus 1 to 1 of f of x plus t minus f of x times the norm of q sub n of t dt. So this is a real number, and it's a real value function, and it's always greater than or equal to 0. So we, the absolute values of it, or the norms of it, itself. So the rest of it I'm going to write down as was. And then I'm going to split up this integral into 3 parts. This integral from minus 1 to delta of f of x plus t minus f of x q n sub t dt plus the integral from minus delta to delta, the exact same thing, f of x plus t minus f of x in norm q times q sub n of t dt plus the integral from delta to 1 the norm of f of x plus t minus f of x times q sub n of t dt. This is going to be less than or equal to, and go from minus 1 to delta of the norm of f of x plus t minus f of x q sub n of t dt plus epsilon over 2 by previous work from minus delta to delta q sub n of t dt plus the integral from delta to 1 of the norm of f of x plus t minus f of x q sub n t dt. true because that middle integral, the f of x, the x plus t, the difference between x plus t and x, which is what we had f applied to, is going to be equal to t, and t's in between minus delta and delta. So the absolute value of t, or the norm of t, is less than or equal to delta. And for that situation, we had that f of those types of things is going to be, the absolute value of that's going to be less than epsilon over 2. Okay. This is going to be less than or equal to. Now this guy is going to be bounded by 2 times the maximum. Well, I guess I can slow this down just a little bit. This interval from minus 1 to delta. Okay. What's bigger than this is the absolute value of f of x plus t plus the absolute value of the norm, shouldn't say absolute value, of x, that times q sub n of t, dt, plus this epsilon of 2 times the interval from minus delta to delta of q sub n of t dt, plus, here I'll do the same thing using the triangle inequality. That's the norm of f of x plus t plus the norm of f of x times q sub n of t dt. And now we can use that maximum, that m, that soup, m equal to that soup. We're almost done with this group. So that's less than or equal to 2m identical from minus 1 to delta of qn sub t plus epsilon over 2 an integral from minus delta to delta of q into t dt, you have dt here, plus an integral from, this is minus 1, I've made a mistake every time, this is minus 1, or I made it here, to minus delta. Now, I made it in the previous line too. Let me go back. Sorry. Right here. This should have been minus delta here and here. So those were typos. Make those corrections. Sorry. Okay. Here's the integral from delta to 1. We have that 2m. Right. So I need the 2m again. Delta to 1, q sub n of t dt. Okay. So this will be less than or equal to 2m times the square root of n times 1 minus delta squared raised to the n. Plus epsilon over 2. Here, this is this integral is going to be less than 1. Replace it with 1 plus 2m and n times the square root of n times 1 minus delta squared raised to the n. That's what that is. Okay. And so since the limit as n goes to infinity of the square root of n times 1 minus delta squared raised to n equals to 0, there exists a natural number n such that for all n bigger than or equal to this big N, 4m times the square root of n times 1 minus delta squared raised to n will be less than epsilon over 2. And so, for all n greater than or equal to this big N, what we'll have is P of n minus f, P sub n of x minus f of x, will be less than epsilon, and that's true for all x. So, that means that the sequence of P sub n's converge uniformly to f. All right. Well, we're through with that subcase, and that's the main thing. Just a little bit more. Okay. So subcase 2 was if f of 0 does not equal to 0 or f of 1 does not equal to 0, then consider g of x equaling to f of x minus f of 0 minus the x times the quantity f of 1 minus f of 0. And you can quickly note that g of 0 will be equal to 0. This is f of 0 minus f of 0. 0 times something 0. And g of 1, this is going to be f of 1 minus f of 0. Of course, that's there, and this is just 1, so we're subtracting the same thing from each other, so that's 0. So g is obtained by a limit of uniformly convergent polynomials. Let's say P sub n, and that's by what we did in subcase 1. Thus, f is the limit of uniformly convergent sequence of polynomials namely, okay, so here's what I'm going to use. I'm going to use P sub n minus, P sub n plus, I should say, f of 0 plus x times f sub 1 minus f sub 0. We have one more case, very simple case to consider. So case 2. Suppose A is different from 0 or B is different from 1. Remember, we had the interval being from 0 to 1 is what we considered in the first case. So we're going to define G acting on 0 to B minus A by G of x is equal to, remember, f's defined on A to B, And so here it's going to be x plus a. Now we're going to find a function L of x on 0 to 1 by L of x is going to be equal to g evaluated b minus a times x. Okay. Then, by our previous work in case 1, now L of x is the limit of uniformly convergent sequence of polynomials p sub n of x on 0 to 1. So working backwards, we have, so g is the limit, I'm not going to write all this down, limit of the sequence p sub n of x star, where p sub n of x star is defined to be p sub n evaluated b minus a times x. Thus, f is the limit of uniformly convergent sequence polynomials. Then step over here. I call it p sub n double star of x equals to p sub n star acting on x plus a. That's the proof of Weierstrass approximation theorem, and that's definitely enough for today. Thank you very much.